Hello, I'm Ryan Kinchin with High Desert Math Tutor, and today I want to talk to you about trigonometric identities. So to begin, we should refresh our memory. What is an equation? So an equation is a statement. We're saying something that is either true or it is false. So in this equation right here, what we're saying is this scary looking thing is the same as 2 cosine. Over here, what we're saying in this equation is this scary looking thing is the same as 1. They have the same value, or they act the same way. So every equation is a statement that's telling you two things are the same, but what's key is to really keep that in mind when we're starting the process of establishing identities, showing that these two things are in fact equal everywhere. So jumping right into how we get started, anytime we are trying to show that this identity is true, we want to take the scarier looking side and do one of two things. First thing is if that side is written in terms of, say, tangent, cotangent, secant, cosecant, we typically want to rewrite those functions in terms of sine and cosine, which in this function we see everything on this left side is already written in terms of sine and cosine. So other than beginning by turning functions like what we see over there into an equivalent function with only cosines and sines in it, the second thing we do is we always take the scarier looking side and we want to try to combine the pieces together to see if anything can cancel out. So how we start is we always want to take the scarier looking side, which for this example is the left side, and we want to copy that down below. So we know that sine theta over 1 plus cosine theta plus 1 plus cosine theta over sine theta. We know, as I mentioned, that everything's in terms of sine and cosine. So the first step we should follow through with here is to try to put these fractions together. But whenever you combine fractions with numbers or with functions, we always need to begin by getting a common denominator. So we can ask, what does this denominator have, which this denominator is missing? This denominator is missing a sine theta. So we're going to multiply by sine theta, but whatever you do to the bottom of the fraction, we have to do to the top. Now we look at this and we ask, what does this denominator have, which this one is missing? Well, this one is missing 1 plus cosine theta. And whatever we multiply the denominator by, we have to multiply the numerator by. So now we can go ahead and just multiply the numerators, but what we'll do in this instance is we're going to leave the denominators alone. So we can put everything over one common denominator now, since we have sine times 1 plus cosine theta, sine times 1 plus cosine theta, that's going to go ahead and stay the same. So sine theta times 1 plus cosine theta. Okay, so we have that. Next, we have sine theta times sine theta, which that ends up becoming sine squared theta. We have addition here, so I'm going to just carry the addition down. And everything in this numerator that we're going to multiply, we need to combine on this side of the plus sign. So we have 1 times 1 is 1. 1 times cosine theta is cosine theta. Cosine theta times 1 is another cosine theta. And finally, cosine theta times cosine theta is positive cosine squared theta. Okay, so now what we can do is start combining any pieces that can be combined, simplify a little bit. So I see here there's a sine squared theta. I'm going to go ahead and just bring this right here. Sine squared theta. I see that there's a cosine squared theta, so I'm going to move that over here. And I'll cross some of this off as we go. So sine squared, cosine squared. They're not canceling, but I'm just showing that I've already counted those. Then here we have 1 plus 2 cosine thetas. So 2 of cosine theta. In the denominator, we still have sine theta times 1 plus cosine theta. Okay, so let's step back, see what we've got for a moment. So what I see is an identity. Sine squared theta plus cosine squared theta. If you recall, sine squared theta, which it doesn't matter if you have theta inside, if you have x inside, as long as we have sine squared with an angle plus cosine squared with the same angle, that's always equal to the number 1. That's one of those fundamental identities. Many people call it the Pythagorean identity that you'll use almost more than anything else. So what we're going to do is we're going to replace this right here with a 1. So we have 1 plus, here's another 1, plus 2 cosine theta. And in the denominator, we have sine theta times 1 plus cosine theta. So see, a key thing you'll see in just a moment is often in the denominator, if something's factored, so it's being written as multiplication, but it's not necessarily, it hasn't been distributed and actually multiplied out, this is usually the form we want to keep denominators in because it lets us see if there's anything we could possibly cancel at some point. So next what I want to do here is combine these two 1s, and what we see is we have 2 plus 2 cosine theta over sine theta times 1 plus cosine theta. And we're so close to the end. So I will squeeze in one more equation here and then put our final answer off to the side. But if you notice, we have a 2 in this term and a 2 in this term. We can factor out a 2. And what's left in the numerator after we factor out the 2 is 1 plus cosine theta. And the denominator is sine theta times 1 plus cosine theta. Now, I hope you can see it still, but what do we have here? We have a common factor in the numerator, and we have a common factor in the denominator. 1 plus cosine theta, these factors cancel each other. And what do we have after this? We see all that's left in the numerator is the number 2. And all that's left in the denominator is sine theta. So the last thing we can do, and I'll just take a baby step here for you, is show that the 2 can go off to the side. This is the same as 1 over sine theta. And finally, what is 1 over sine theta equal to? Well, if we look it up, that's actually equal to cosecant theta. Now, let's just evaluate this for a moment. We started with this monster of an expression, sine over 1 plus cosine theta plus 1 plus cosine theta over sine theta. We took that piece and we started asking ourselves, how can we combine these pieces? Well, since we had two fractions, we decided to start by getting a common denominator. We put this together into one giant fraction. We moved the pieces around and simplified a little bit, and we saw that we have a sine squared plus cosine squared, which, as we should recall, that's the Pythagorean identity, that's always equal to 1. So we replaced that with the number 1. Then we took the 1 we already had with this new 1 that we have, combined them. We saw we could factor out a 2 from the numerator, and at that point we saw we have a common factor in the numerator and the denominator, which we could cancel. We canceled those factors, and we got this much simpler looking fraction. Then, just for fun, I showed you, very explicitly that this 2 can be taken off to the side. It's still being multiplied, but we literally have 1 over sine theta, which is by definition cosecant theta. So one more example now of establishing a trigonometric identity. Remember, our goal is to show that the left side of this equation is the same as the right side of the equation. One thing I should mention, I wanted to do this before, but I forgot, is I want to really establish the fact that we're starting with one side of the equation, and then we're taking small steps that are very manageable to connect the left side of the equation ultimately to the right side of the equation. So we're just starting with only one side and working our way through that side, taking correct algebra steps to show that we can work our way to the other side of the equation. Now, in this problem here, what we want to do is start by rewriting anything with tangent, cotangent, secant, cosecant. We want to start by writing those in terms of only sines and cosines. But just recall, we're always going to start with the scarier looking side. So we have tangent v plus cotangent v over secant v times cosecant v. And I'm going to write this one in the proper format that I typically write problems in. It's very standard to always start on the top left, work to the right, and from there, work your way down to the final answer. I didn't have enough space for this side, so I decided just to go straight down initially. But what we're going to do here is rewrite tangent v as sine v over cosine v plus, now cotangent is cosine v over sine v. That's our numerator. We still have our large fraction bar. The denominator, secant, is by definition 1 over cosine v times cosecant, by definition, is 1 over sine v. Okay, so we've gotten started by rewriting all the trig functions in terms of sines and cosines. And it's okay if there are other numbers and operations mixed in. It's just the functions need to only have sines and cosines. So the next step, as we saw here, is we want to start combining anything we can combine. And if you have two fractions, that's usually a good place to start. So we can look here and ask, what does this denominator have that this one is missing? This denominator has sine v. So I'm going to multiply this whole fraction by sine v over sine v. Now, what does this denominator have that this one is missing? This has a sine and a cosine, so we need a cosine over here. So multiply by cosine v over cosine v. And really, we don't need to worry about doing anything in the denominator at this point. We just need to focus on one thing at a time, so we'll focus on combining the numerators. Now, we can go ahead and turn this into one big fraction in the numerator. We have a sine times a cosine times a cosine. So everything is going to be over sine v times cosine v. But for our numerator, sine v times sine v, that's sine squared v, plus cosine v times cosine v is cosine squared v. Now this may look like we're done, but don't forget, this is just the numerator of this larger complex fraction. So we still have 1 over, and I'll go ahead and actually combine this now, sorry. So we see in the denominator, 1 times 1 is just 1, but we still have cosine. I'm going to switch these around also, where I put the sine on the left, sine v, times cosine v. So just remember, the commutative property lets us move things around as long as we're multiplying. So I decided just to swap the sine and the cosine so that the sine's on the left. So now, a couple more things we can do. There are 2 ways we can look at this, but I will do this in a kind of interesting way. Notice that we have, just as we had in this problem, sine squared plus cosine squared, sine squared plus cosine squared. This whole numerator is equal to 1. So sine squared plus cosine squared is 1. In the denominator, we have sine v plus cosine v. Sine v, oh, not plus, I'm sorry, sine v times cosine v. We have our large fraction bar. And then in the denominator, 1 over sine v times cosine v. So one thing I've always found to be very kind of interesting, entertaining when you're doing math is you take a very simple idea and you apply it to something really insane looking. So if you remember, for division, anything divided by itself is always equal to 1. Well, I see 1 over sine v cosine v divided by 1 over sine v cosine v. That looks like something divided by itself. So this, in fact, is equal to 1. And if we look back at the original problem, this, we wanted it to be equal to 1. And that's what we've established. But let me just show you off to the side, kind of more step by step what you can do if that's a little bit not obvious. So whenever you're dealing with fractions and fractions, we can always follow the rule to keep the numerator the same, change division to multiplication, and flip the second fraction. I'm going to do that sort of in 2 ways. So first I'll show you how to write this as 2 different fractions. So we have 1 over sine v cosine v, 1 over sine v cosine v. Now this big division bar, we can literally write divided by. Then the denominator is still 1 over sine v cosine v. But now, back to that rule I mentioned a moment ago, we can keep the first fraction the same, 1 over sine v cosine v, change division to multiplication, and then take the reciprocal, or flip the second fraction. That whole thing is over 1. Now, what can we cancel here? Notice we have sine times cosine in the denominator here, sine times cosine in the numerator there. Those 2 things cancel. What we have left over in the numerator is just a 1 from here divided by a 1 from here, and 1 divided by 1 is 1. So we have established, by taking small logical steps, that tangent v plus cotangent v over secant v times cosecant v, that's actually the same as just 1. So that was solving trigonometric identities, or establishing identities, proving the identities. Just to reiterate, the 2 things you want to do to get started always. If you have functions written in terms of tangent, cotangent, secant, or cosecant, you want to begin by rewriting those in terms of sine and cosine most often. Not always, but most often. After everything is in terms of sine and cosine, you just start combining anything you can combine. If you have fractions, get a common denominator. Then when things start to be combined, we want to look for any trig identities that we are certain are true. And one of the most important useful identities you can ever use is sine squared plus cosine squared equals 1. Just remember, we still need the angles, and these two angles have to be the same angle. But this Pythagorean identity is indispensable. We need that in most of these problems. Finally, after we cancel anything we can cancel, sometimes we have to use another fundamental trig identity to actually get the final answer, which is the right side of this original equation. So that's solving trigonometric identities.